In the vast and ever-evolving landscape of military aviation, where technological leaps often define the balance of power between nations, the McDonnell Douglas F-15 Eagle stands as one of the most iconic and enduring success stories of the late 20th century. Introduced into United States Air Force service in January 1976, the Eagle was designed from the outset as a pure air superiority fighter, built around the mantra, "Not a pound for air-to-ground," emphasizing speed, maneuverability, radar capability, and overwhelming thrust-to-weight ratio that allowed it to dominate the skies in ways few contemporaries could match. Its combat record remains flawless to this day, with over 100 aerial victories and 0 losses in actual engagements across multiple conflicts involving Israeli, Saudi, and American pilots. However, even this near-perfect platform carried an Achilles heel that became glaringly obvious as Cold War tensions escalated through the 1970s and into the 1980s. Its dependence on long, high-quality runways for safe takeoff and landing operations. In a hypothetical large-scale European theater war against the Warsaw Pact, Soviet military planners had long prioritized the neutralization of NATO air power through preemptive strikes using SS-20 missiles, Su-22M backfire bombers, and Su-24 Fencer tactical aircraft equipped with precision-guided munitions designed specifically to crater runways and destroy taxiways. Once the runways were damaged beyond quick repair, even the most advanced fighters sitting in hardened aircraft shelters would become useless sitting ducks, unable to generate sorties when they were needed most. This vulnerability prompted the USAF to initiate a series of studies and programs aimed at developing high-performance fighters with genuine short takeoff and landing (STOL) capabilities, ideally capable of operating from austere, bomb-damaged strips as short as 1,500 feet, in crosswinds up to 30 knots, at night or in poor weather, and without reliance on ground-based instrument landing systems or radar vectors. Among the technologies explored, thrust vectoring, the redirection of engine exhaust gases to produce additional lift, control moments, or deceleration, quickly rose to the forefront as the most promising path forward for maintaining supersonic performance while achieving revolutionary short-field characteristics. Unlike earlier V/STOL concepts such as the subsonic Harrier jump jet, which sacrificed top speed and payload for vertical capability, thrust vectoring in a high-thrust supersonic fighter promised to retain air dominance traits while adding battlefield survivability through dispersed operations. The F-15 Eagle, with its twin Pratt & Whitney F-100 engines delivering dry thrust in excess of 25,000 pounds each and afterburning thrust approaching 50,000 pounds combined, offered an ideal starting point due to its already impressive excess power and robust airframe designed to withstand 9G maneuvers and high dynamic pressures. Recognizing this potential, the Air Force Flight Dynamics Laboratory at Wright-Patterson Air Force Base, in collaboration with the Aeronautical Systems Division, launched the STOL/Maneuver Technology Demonstrator Program in the early 1980s, culminating in a 1984 contract award to McDonnell Douglas for the modification of an existing F-15 airframe. The aircraft selected was no ordinary production Eagle. It was serial number 71-0290, the very first two-seat TF-15A, later redesignated F-15B, ever built, which had rolled off the assembly line in 1973 as a pre-production prototype and had already served as a flying testbed for avionics integration during the development of the F-15 E-Strike Eagle variant. This history made it particularly suitable for further experimentation, as its systems were well characterized. It had accumulated significant flight hours, and its structure had demonstrated ample margin for additional modifications without requiring a complete redesign. The transformation into the F-15 STOL/MTD involved an array of exotic and groundbreaking changes that turned the familiar twin-tail fighter into something far more unconventional. Central to the modifications were the installation of two-dimensional thrust vectoring and thrust-reversing nozzles on the F-100 PW-100 engines, later upgraded, capable of deflecting the exhaust plume up to 20 degrees in the pitch axis for both upward lift during takeoff and landing phases and downward deflection for enhanced pitch control at high angles of attack. These nozzles could also partially close to produce reverse thrust, initially demonstrated in ground runs and later in flight, providing an unprecedented airborne deceleration capability equivalent to a massive speed brake without the drag penalties associated with traditional aerodynamic devices. To complement the vectoring nozzles and address pitch authority at low speeds, where the conventional horizontal stabilators lost effectiveness due to blanking or shock-induced separation, engineers added small Canard foreplanes mounted forward of the main wings. These Canards were not newly designed but cleverly adapted, or as some wryly described it, Frankensteined, from surplus F/A-18 Hornet horizontal stabilators, which provided excellent all-moving control surfaces with proven high AOA characteristics. The Canards were integrated into the flight control system to work in harmony with the nozzles, generating direct lift for short takeoffs and counteracting any adverse pitch moments created by upward vectoring. Perhaps the most sophisticated aspect of the entire modification package was the implementation of an advanced digital integrated flight and propulsion control system, or IFPC, which used fly-by-wire architecture to blend inputs from aerodynamic surfaces, ailerons, rudders, stabilators, with nozzle deflections and engine thrust commands in real time. This system employed model-following control laws, where pilot commands were interpreted through a reference model that dictated desired aircraft response, and the computer continuously adjusted surface and nozzle positions to achieve that response with minimal pilot workload, even in highly nonlinear flight regimes. Additional enhancements included strengthened main landing gear struts to handle higher sink rates on short, rough fields, advanced anti-skid braking systems tuned for reverse thrust landings, modified fuel system plumbing to manage center of gravity shifts during vectoring maneuvers, and an extensive suite of instrumentation including strain gauges, pressure transducers, accelerometers, air data booms, and high-speed data recorders to capture every nuance of the aircraft's behavior for post-flight analysis. The program goals were nothing short of revolutionary for a supersonic fighter. Demonstrate routine takeoff and landing operations within a 1,500 by 50-foot damaged runway segment under simulated combat conditions, including wet surfaces, obstacles, and 30-knot crosswinds. Achieve autonomous landings using onboard sensors without external aids, and preserve the baseline F-15's Mach 2 plus capability, 9G maneuver envelope, and weapon-carrying potential when the special STOL features were not in use. Following extensive ground testing of the vectoring nozzles and Canard integration, the modified F-15 STOL/MTD lifted off for its maiden flight on September 7, 1988, from the dry lake beds of Edwards Air Force Base in California, piloted by McDonnell Douglas test pilot Larry Walker. Initial flights focused on envelope expansion with nozzles and Canards locked in neutral positions to verify basic handling qualities remained acceptable. Within months, however, the true potential began to emerge as vectoring was gradually introduced. Takeoff demonstrations quickly shattered expectations, with the aircraft lifting off at ground speeds as low as 42 miles per hour under light load conditions, a velocity slower than many automobiles cruising on American highways, thanks to the combination of downward nozzle deflection generating additional upward force at the tail and Canard lift pulling the nose up at extremely low dynamic pressures. Rollout distances for takeoff were reduced by 25 to 35% compared to a standard F-15, and in some configurations, the jet became airborne after less than 300 feet of ground run. Landing performance proved equally astonishing. By deflecting the nozzles upward to produce nose-up pitching moment and direct lift, deploying the Canards for additional pitch authority, engaging partial reverse thrust in flight to bleed off speed rapidly, and then applying wheel brakes upon touchdown, the aircraft consistently achieved full stop distances of around 1,650 feet on dry concrete, representing an approximately 80% reduction from the baseline Eagle's typical 8,000-foot landing roll under similar conditions. The in-flight reverse thrust capability was particularly innovative and daring, allowing the pilot to decelerate from approach speeds of 200 knots or more down to landing threshold velocity in a matter of seconds, functioning as an aerodynamic brake far more efficient than speed brakes or drogue parachutes used on other aircraft. By January 1989, The program had progressed to Phase 1 autonomous landing demonstrations, where the jet successfully touched down on simulated bomb-damaged runways featuring uneven surfaces, standing water, and debris, using only onboard laser altimeters, radar altimeters, inertial navigation, and computer-generated glide path commands. Crosswind testing pushed the limits further, with stable landings recorded in gusts up to 35 knots, well beyond what most production fighters could handle safely. High angle of attack testing revealed the synergistic benefits of canards and vectoring, enabling controlled flight at angles exceeding 50 degrees where conventional tails would stall or lose effectiveness due to flow separation. Over the course of 3 years, the STOL/MTD accumulated more than 400 test sorties, generating terabytes worth of data, in modern terms, on integrated propulsion aerodynamic control, nozzle durability under repeated deflections, engine performance during reverse thrust transients, and structural loads induced by asymmetric vectoring or rough field operations. When the USAF-managed portion of the program concluded in August 1991, the aircraft had conclusively proven that thrust vectoring combined with canards and digital controls could transform a high-performance fighter into a battlefield survivable asset capable of operating from dispersed, damaged locations without sacrificing its core mission effectiveness. Rather than scrapping the valuable testbed, NASA took possession of the airframe on June 15, 1993, transferring it to the Dryden Flight Research Center, now Armstrong Flight Research Center, at Edwards AFB for a new phase of experimentation under the designation NF-15B ACTIVE, where ACTIVE stood for Advanced Control Technology for Integrated Vehicles. This transition marked a shift in emphasis from primarily short-field survival in a tactical combat scenario to broader exploration of high-performance maneuverability, supersonic thrust vectoring, drag minimization, and adaptive flight control concepts that could benefit future fighter designs across the board. Major hardware upgrades were implemented during the NASA refurbishment period. The original F-100PW-100 engines were replaced with the more powerful F-100PW-229 variants, which offered increased dry thrust, improved afterburner efficiency, and better compatibility with vectoring nozzles due to enhanced turbine cooling and material durability. The two-dimensional pitch vectoring nozzles were removed and supplanted by fully axisymmetric pitch/yaw balance beam nozzles, PYBBN, which were round in cross-section and capable of independent deflection up to 20 degrees in both pitch and yaw axes simultaneously, providing true multi-directional thrust vectoring without the mechanical complexity or weight penalty of earlier 2D designs. The flight control system was completely overhauled to a fully digital fly-by-wire architecture with triple redundant processors, reconfigurable control laws that could be uploaded from the ground between flights, and a dedicated research flight computer allowing engineers to test experimental algorithms in real time without risking the primary flight controls. Instrumentation was expanded dramatically to include high-bandwidth strain gauges on the nozzles and canards, flow sensors in the engine inlets to monitor distortion during vectoring, optical pyrometers for nozzle temperature monitoring, and video cameras mounted on the vertical tails to capture exhaust plume behavior at high Mach numbers. The ACTIVE program's objectives centered on demonstrating the feasibility of sustained thrust vectoring in transonic and supersonic flight regimes, where aerodynamic control surfaces suffer from reduced effectiveness due to compressibility effects and shock wave interactions, reducing cruise drag through vector trim techniques that replaced large surface deflections with small nozzle adjustments. Exploring post-stall maneuverability and recovery techniques using integrated propulsion control, and developing fault-tolerant control strategies that allowed continued safe flight even if primary aerodynamic surfaces were damaged or jammed, relying instead on differential engine thrust and nozzle modulation. Flight testing resumed in earnest in 1996 after extensive ground vibration, structural, and engine runs. On March 27, 1996, the first axisymmetric vectoring flight occurred, followed by the historic milestone on April 24, 1996, when the NF-15B ACTIVE became the world's first aircraft to achieve controlled yaw vectoring above the speed of sound, using nozzle deflections to generate side force and yaw moment at Mach numbers greater than 1.0 without rudder input. This breakthrough was significant because at supersonic speeds, traditional vertical tails lose authority due to shock-induced flow separation, making yaw control particularly challenging without vectored thrust. The program reached its most impressive peak on October 31, 1996, when full 20-degree yaw and pitch deflections were demonstrated at Mach 1.95, approximately 1,300 miles per hour, under conditions of intense aerodynamic heating and dynamic pressure that pushed nozzle materials and actuation systems to their limits. Ground tests had previously confirmed the structural integrity of 20-degree deflections at Mach 2, but in-flight validation represented a quantum leap in propulsion-integrated control. Throughout 1996 to 1999, the aircraft routinely flew aggressive post-stall maneuvers, including velocity vector rolls, high-alpha nose pointing, and controlled departures and recoveries at angles of attack exceeding 70 degrees, where the aerodynamic center of pressure shifted dramatically and conventional stability margins vanished. These maneuvers were not performed for airshow spectacle but for rigorous data collection, allowing engineers to validate mathematical models of post-stall aerodynamics, refine control allocation algorithms, and quantify the benefits of thrust vectoring in extending the usable flight envelope. One particularly valuable demonstration involved propulsion-only control, where pilots intentionally disabled or simulated failure of aerodynamic surfaces and flew the aircraft solely using differential thrust, nozzle vectoring, and throttle modulation, a capability that foreshadowed later research into damage-adaptive flight controls for combat-damaged aircraft. The integration of propulsion and aerodynamic controls achieved remarkable harmony. At low speeds and high angles of attack, thrust vectoring provided 60 to 80% of the required pitching and yawing moments, while at high subsonic and supersonic speeds, aerodynamic surfaces took over the majority of the workload to preserve nozzle life and minimize mechanical wear. This blended approach, governed by adaptive control laws that switched modes based on Mach number, angle of attack, altitude, and dynamic pressure, resulted in handling qualities that pilots described as extraordinarily precise and forgiving even in extreme conditions. Quantifiable performance gains included cruise drag reductions of 15 to 20% through vectored trim, subtle nozzle deflections that maintained trimmed flight with smaller elevon or rudder inputs than traditional methods, leading to improved fuel efficiency and extended range in loiter or transit missions. Structural loads were also reduced in many flight regimes because vectoring allowed smoother control inputs without large surface deflections that induced buffet or flutter risks. Technical challenges abounded throughout the program.